Okay, so what we're going to do now in this video is we're going to talk about inverse functions. So integrals resulting in inverse trigonometric functions. Okay, so this is going to bring up some things that you should have learned in prior classes. Okay, so when we deal with trigonometric functions, one thing we have to realize is that trigonometric functions are not always one-to-one unless you restrict the domain. So it's very very important that we consider the domain when we're working with inverse trigonometric functions. So that being said, we've also learned about some of these derivatives, okay, of trig functions. Okay, and so we're going to use also some of the trig properties, okay, trig identities and things like that that are going to help us. Okay, so here are 3 rules that you're going to want to learn. Okay, you're going to want to learn these and make sure you learn them, because this is going to be important. It's going to make things a lot easier if you just memorize them. So again, make sure that you consider the restrictions. Okay. Also, make sure you understand the derivatives of inverse functions. Okay, again, so I don't know how you did or what your study habits were in Calc 1, but in Calc 1 you went over and covered derivatives of inverse trig functions. You should know those. Okay, you should know those. Okay, so these are the 3 rules. So if we integrate this, if you have something of this form, it's going to give you inverse sine of u over a. And if you have this form and you integrate it, it's going to give you this antiderivative. And if you have this, then it's going to give you this as an antiderivative. Okay, so again, memorize the forms, because that's going to be important, trying to see if it fits one of those forms. Okay, so I'm going to do a proof of proving that these do work. Okay, so let's do the first one. Okay, so if I want to prove that this is true, okay, that the antiderivative of this is equal to this. So first of all, I'm going to start with defining y, a function. Okay, so I'm going to define y. So let y equal sine inverse of u over a. Okay, or actually, let's just put it with x and y. I don't want to, let's just do x. Let's just keep it as a function of x. Okay, so let y equal sine inverse sine of x over a. And so if I take the sine of both sides, right? So if I take the sine of both sides, so now we're just going to simplify this. And so I want to take the sine of both sides. And so if I do that, I get a sine y equals x. Okay? And now what I'm going to do is I'm going to use implicit differentiation on both sides. So I'm going to implicitly derive. Okay? So what I'm going to do is I'm going to take the derivative of both sides with respect to x. Okay. So what does that give me? Well, that gives me what? So if I take the derivative of this thing, well, a is a constant, so that's just going to be pulled out. So I'm going to get a. And then here I have sine of an unknown function of x, y. So what I'm going to do is this is going to use the chain rule. So it's going to be a times the derivative of the outside, which is going to be cosine y, times the derivative of the inside, which I don't know what that function is. That's why we're doing implicit differentiation here. So I'm going to just write it as dy dx. Okay, this should be review. And then this side is just going to be 1. Okay, so now, that means dy dx equals what? 1 over a cosine y. Okay, so far so good. So again, make sure you pause and you understand. Okay, so now, again, remember the goal. We're trying to show these two are equal. Okay, so now, I know that dy dx is equal to this. Okay, now, one of the identities that I'm going to use, because we're dealing with trig identities, one of the identities that I'm going to use is the Pythagorean identity, which is sine squared x, sine x squared plus cosine x squared equals 1. And so what I'm going to do is I'm going to solve for cosine. So that means cosine x equals the square root of what? 1 minus sine squared x. Okay. So now what I'm going to do is now I'm going to substitute in for cosine y. Okay, so all I'm just going to do is use the Pythagorean identity and replace y. Now again, I just did it in x, but I'm going to do it here in y. So let's go over here, and so let's write this. So it's going to be dy dx equals 1 over a times the square root of 1 minus sine squared y. Okay, so now it's starting to look like this. Okay, so I started with this side, and I'm taking the derivative, right? This is equal to y, and I took the derivative of both sides, and I'm trying to get to this right here, because if I can show that the derivative of this gives me this, I'm done. So now what I'm going to do is I'm going to distribute the a inside the radical, so that means I'm going to square it. So this gives me 1 over the square root of a squared minus a squared sine y. Okay, now, cool thing happens. Sine squared y. Now, cool thing happens. Well, what is this? Let's simplify it a little bit more. This is a squared minus a sine y quantity squared. So what's a sine y though? Right here. We defined, right? We defined y equals this, which means x equals this. Well, we just got it. So guess what? We got 1 over the square root of a squared minus x squared. And we're done. We got it. That's the proof. Okay, that's it. Have a great day, and next video we'll start doing some examples.